There you go. Okay, so today we will talk about, this lecture is essentially about file systems, okay? And we're going to use this classic paper called the Unix time sharing system as a pretext to set up the background for all the concepts that we are discussing, okay? So the Unix time sharing system, this was, the Unix operating system itself was developed by two people, Ritchie and Thompson from Bell Labs. And at the time they did this, Bell Labs was at the forefront of a lot of new innovations in computer science. And these guys, being part of Bell Labs, they were deeply involved in both the Multics operating system, which preceded this, and in the Unix operating system that they developed from scratch. So, and you will, throughout this lecture, you will see that, how all the, even Linux operating system that we use now, how it has been heavily influenced by the original design of the Unix system by Ritchie and Thompson. Okay, as you can see from the date, it's like July 1974, before most of you were even born. I was 2 years old at that time. So, but then the reason why we're discussing such an old paper is because some of the basic abstractions that they developed at that time, they were so elegant and so general purpose that they've stood the test of time. Even today, many of the system calls you learn about, things like fork, pipe, exec, all these were originally conceived by Ritchie and Thompson. So let's get going. I am not sure what I'm doing wrong, but I'm gonna. Right. Okay. So this is an overview of the motivation behind why they developed. So there is the original paper is also online posted, and I highly encourage you to read it because the way they describe their system, it will give you insight into their thinking. So the way they motivate is that they set out to develop a general purpose multi-user interactive operating system. Now these things sound very generic terms for us now, but at that time these were revolutionary. What does that mean? Like, a general purpose computer means that it should be capable of running any program meant for any purpose, right? But that was apparently a novelty back then. Computers were specialized, or they were not general purpose enough. And then multi-user, like back then, it was again a novelty. The idea that more than one user should be able to use a computer at the same time. Like, all of you log into remote.cs and use the same machines without being aware of each other, right? Back then, only one user could use these giant mainframes at a time. So the idea of having a multi-user operating system was novel. And the fact that operating system needed to support interactive services, again, that was novel. Like, earlier you would have batch jobs. You'd take a bunch of punch cards, feed them into the computer, to this giant computer, and the computer would execute the program and out will come the output. But in between, you can't interact with the programs to change its behavior. So the idea of interacting with your program as it's executing, that was new. So assignment 1 that you developed on the Unix shell, right? That's an interactive program. It asks you for command to execute, gives you the output, it gives you the ability to control the jobs. So all that ideas weren't present at that time. So these guys came up with these ideas and actually implemented it. So they originally implemented it on the DEC PDP 7, 9, and 11 computers. These were leading mainframe systems at the time, and these guys had access to it. And they give some specifications of this computer, which was kind of interesting. You can see that it had an 8-bit byte computer, because before that there used to be 7-bit byte computers as well. And then its main memory had a grand total of 144 kilobytes of DRAM. Wow. That was a lot back then. And now even if you write a hello world program, it may not fit 144 kilobytes. But back then, that was a lot of memory, of which the Unix operating system occupied 42 kilobytes. Now, just imagine that, if you check the memory usage of your current operating system, you would see it's easily occupying 100 megabytes or more. Actually, getting an OS to use Linux to use less than 100 megabytes is challenging. You could try it, but and if you can do it, that would be pretty awesome. But back then they implemented the whole Unix OS in 42 kilobytes. Of course, now the operating systems also do a lot more. And then it had a 1 megabyte fixed head disk. Again, that was a pretty cool thing back then. A 40 megabyte disk pack. Not just that, there was backup storage. And then they don't stop there. They go on to describe, there was a picture phone, camera. Their computer had a camera. There was voice response, speakers that could talk back. There was a voice synthesizer and a photo typesetter. You could do word processing on these. And a digital switching network. Not just that it could talk to other computers, right? But then they were not happy with the operating system that was running on it. It was not making use of all these features. So they wrote their own operating system. It was written in C language. And then since then, the Unix operating system has evolved. There have been many variants of it developed. And System 5, FreeBSD, Solaris, Linux, and of course, Mac OS. These are some of the predominant variants of Unix. And apparently the latest version of Windows also has a Unix-like kernel, which is amazing. All right. Any questions so far from anyone? Okay. So let's get back to the presentation. So, the very first thing they mention in the paper is that one of the biggest innovations in their operating system was a hierarchical file system. They don't say, that the CPU scheduler or memory management is the most innovative thing. They point out that the file system, hierarchical file system, was the most novel part of their Unix operating system. Right, which is kind of surprising. You can usually think of file system as a boring thing, right? It stores files and folders, and you have to organize, drag and drop stuff. But for them, this was like the most coolest part of their whole OS, and we'll see why. So they could treat normal files, IO devices, and interprocess communication through a same common interface of a Unix file system. They had the ability to do interactive jobs, so they could run background jobs like batch processes, but they could also do foreground jobs in which you can type input and then get output from the program as the program is running. And they had a shell. The shell was a brand new idea that these guys developed, where you could have such interaction, that could enable such an interaction. Okay. So so of course they were working for Bell Labs, and AT&T Bell Labs was AT&T is a telephone company, right? So if they're doing all this operating system development, they had to justify to their parent company why they are doing this work. So then their reasoning is that this operating system will be used for preparation and formatting of patent applications and other textual materials. Right? Because presumably AT&T was publishing a lot of patents, and they say, hey, we'll make it easier for you to type your patents and publish them, right? And edit them. It will become faster, so you can have more patents, right? And then, of course, since this is a telephone company, they used to handle user complaints. So, user problems, ticket processing. So there's a collection and processing of troubled data from switching machines, from possibly users, recording and checking telephone service order. So they're trying to relate their work to the mission of their parent company, right? And it seems quite narrow, but of course they had their own agenda in developing this OS. Because in the beginning they said there's going to be a general purpose operating system. So now, as you can know, that Unix or its variants are widely used in servers, desktops, laptops, notebooks, and so on. Pretty much even switches and routers. That, you know, if you have a small Wi-Fi router sitting on in your house somewhere, that's possibly running Unix, right? Your phones are running Unix. Android is a variant of Linux, which, you know, is a variant of Unix, and so forth. So pretty much Unix is everywhere. You can safely say that it has taken over the world, right? Starting from that small project by two guys. And it was all written in C. And by the way, C language, these guys developed C language just for the purpose of writing this operating system, right? So they developed the C language, and then they wrote their OS in the C language, which is pretty cool. Okay. So, and then after the previous slide where they give very specific reasons for developing the OS, later on they say, paradoxically, the success is due to the fact that Unix was not designed to meet any predefined objectives, right? So despite the fact that you can do all these things, you can pretty much do anything else with it. So I just go over this history, not to bore you, but to show that, you know, there is, to me, it's very interesting. History of computer science is really provides you a rich perspective. And then they say, oh, Unix can run in a hardware costing as little as $40,000, which is, you know, I'm sure it was chump change back then as it is right now. And it took 2 people 1 year to develop the whole operating system, right? 2 man years. And then they don't say that, oh, you know, if you look at typical systems papers, they will try to make a case of how complicated and how challenging it is to develop. But here they are proud of the fact that it's the simplicity, elegance, and ease of use of Unix that are its defining characteristics, right? So from the very beginning, their goal was to make it everything that Multics was not. Multics was also a very pioneering system, both hardware and software system, but they wanted to address all the drawbacks of Multics in Unix. So they, like I mentioned earlier, they think that the file system was the most challenging, most important component of Unix. And the reason was that before the idea of Unix file system was developed, there were different ways of storing and retrieving data. Depending on the type of data you had different, you know, if you're accessing database records for a particular for use case, you had a certain way of storing files. If you had, you know, some other application, you know, you might have some other format. So there was no uniform way of storing and accessing files on the storage system. There was no common uniform way of organizing these files. And then if you had to access hardware devices, then there was a completely different interface. So these guys wanted to bring all this together. So all of these deal with the usability of the system, and they wanted to bring all of these things together under one umbrella. So which is why they invented the hierarchical file system idea. So under their hierarchical file system concept, there are 3 types of files. There are normal files in which you store normal data. And then there are directories, directories are also files. Actually, you can think of directories as a file which contains a list of other files that it contains, right? It's a recursive definition. So for them, directories are also files. And then any hardware IO device is also a file. So for example, if you have a keyboard or a mouse, it shows up as a file in your file system. If you want to read or write, you know, read from your keyboard or write to your screen, for example, you would just open the corresponding device file and perform read-write IO operation, just like what you're doing with a character device right now in your assignment, right? So it's the same interface they use for normal files and you use for hardware devices. There is no major difference between them. So which was very convenient. You could write an application. In theory, it would work both on ordinary files and on hardware devices. Okay. So by doing this, you get a lot of benefits. Like you did I/O redirection last time from one program to another. The program thinks it is writing to standard output, but actually it is writing into the standard input of another program, right? So so that kind of shows, you could why treating I/O devices as also files is important. Okay. Any questions so far? Again, if you want to speak up, that's perfectly fine. Don't be shy, just like in a normal class. Okay, so I don't see anyone raising their hands yet. All right, so let me go back to talking to myself. So here's one of the cool things that you can do with their files, which is with the hierarchical file system. So and under the idea of a hierarchical file system, what they mean is that all the files in I/O devices, they are part of a single rooted hierarchy. What that means is at the top you have a root directory, and then there are subdirectories, and those subdirectories may have other subdirectories, and so on till you reach leaf nodes, which are the individual files. So when you create a file in Unix, there is, by definition, the Unix does not impose any structure on it. What that means is a file is just a sequence of bytes, right? And as far as the OS is concerned, it doesn't know what those bytes mean. It doesn't care what those bytes mean, okay? So what this implies is that the semantic information, which is what is the meaning of the data inside a file, is up to the user level program. So you, for example, you could create a file that has music, right? An MP3 file, right? But, or you could create a file that has video in it, or that has text in it, okay? But as far as the Unix file system is concerned, internally, it just treats all of them as a sequence of bytes, right? So you might have a type subfield that says, the type of this file is such and such, but really, as far as the Unix file system is concerned, it doesn't care what that type means. So OS is agnostic or unaware of the semantic meaning of the contents of the file, okay? So, whereas earlier, what they would do is, they would, for example, if they're storing user records, then whatever file system they were using, it would be structured around the operations on these records. Like a user record has a name, first name, last name, phone number, trouble ticket information, and so on. So, and then there are ways to organize this information. Somebody has a question? Okay, so I heard someone speaking. If you have a question, that's fine. Just feel free to speak up. Okay. So, all right. So, so this idea that you could organize everything as a hierarchical rooted file system was itself novel at that time. And this was around like mid to late 1960s that we're talking about. And they went beyond that. They said that you could have this idea of a shared file between multiple subdirectories. So in this example, you can see that a subdirectory for user B and a subdirectory for user C, they have a common file, a shared file, which is marked with a question mark, right? So So what does that mean? How can two directories share a file? The idea here is that, say C, it could create a file under its directory, and then the circle at the bottom is the actual file, the content of the file, whereas C itself refers to a piece of metadata or a property of the file. We will later look at this, it's called an inode. So the inode includes information such as C is the owner of the file, and then there is a count, as you can see, the reference count, which says that there is one directory referring to this file, right? So as you can, we again bring back our old friend indirection, to solve the sharing problem, right? So we don't like tie the file to a particular directory. Rather, we have sort of a pointer to the inode, not a memory pointer, but rather a file inode address, which then tells you where the file is. But it also has an extra information that the reference count is initially 1. Later, let's say B wants to share C's file, and assuming B has the permissions to share C's file, B will create an entry in its directory that will refer to the same file that C had created. And when B does that, it's called linking to an existing file. And in this particular case, we're creating something called a hard link. There's something called a soft link, which is different, and we will look at that. The hard link, when you create a hard link, the reference count in that inode goes to 2. So now it means that there are 2 directories listing. So similarly, if another user links their subdirectory, the reference count will go to 3 and so on. Later, C removes its, C pretends to delete the file, but actually the deletion doesn't get rid of the file itself. It just reduces the reference count by 1, as you can see in the figure C in this slide. So finally, if later B deletes the file, then the reference count will go to 0. And at that time, the operating system will actually delete the contents of the file. So what that means is if whenever C makes any changes to the file, this will be immediately visible to B through B's directory, and vice versa. I see that there's possibly some question. I'm still not good at this, but we'll figure this out. Okay. Chat. Okay. So the question from Harshit is, are these shared files different from symbolic links in files? Yeah. So yes, these the links that we are talking about, the sharing of files, is something called a hard link. Symbolic links are something called soft links, and there is a subtle difference between these. So when we do hard links, these usually refer to these are references to the inode of the file, and I'll talk about what inodes mean. They describe the properties of a file, and different users, for example, B could have one name for a file and C could have another name. C may have created the file by the name, say, file1, whereas B could refer to the same file and use a different name, file2, right? But they're both referring to the same file. But the fact that they're referring to the inode of the file on the disk, so the name is kind of meaningless. When you have symbolic links, you again have a file, and then in another part of your file system, you can create a symbolic link, meaning that you could tell the file system that here I'm linking to the other file, just like with a hard link, except that I'm not going to refer to the inode. I'm going to refer to the name of the other file. So with a symbolic link, for the example I just gave, if C created file1, then B would say my file2 actually refers to the name file1 in C's directory. So there's an entire path name being linked rather than the inode, right? So that's why it's called symbolic, because you're referring to the symbol, the name of the other file. And these are less um, they're less consistent because C could delete the original file that will be completely gone. With a symbolic link, C could delete the original file. And then B may still have a symbolic link, but that will be invalid. Later, if C tries to access the file through a symbolic link to a file that was deleted, then that access would fail, right? But with a hard link, the file is kept around because the reference count is incremented. Okay, I don't know if that, does it answer your question, Harshit? Okay, so there's another question from Aditya. How does modification work with shared files? Do one directory get the same modification made by another? Uh, so modification of shared files depends upon the permission. So if in this example, C had given B the permission to modify the file, then B would be able to modify that file. And then whatever modification B makes, C would be able to see them, and whatever modification C makes, B would be able to see them. And of course, what if both of them try to modify at the same time? They could, and as far as typical Unix file systems are concerned, they don't try to solve any race conditions. So if they're trying to access the same file and modify it at the same time, it's a race condition. And the file system has no way to guess what the user wants to do. So they're just going to apply those changes in some non-deterministic order. So, so if users want to have consistency in accessing the same file, they need to use locks or semaphores or some other synchronization mechanism, just as with user shared memory in user level processes. Okay, so does that answer your question, Aditya? Okay, I'm gonna assume that it does. Okay, so Anurag is asking a question. Are these hard links created only when a single file is shared among two or more users, or also created when a file is copied from one user to another? Yeah, so the hard links are created when you want to share a file. Like you don't want to make a copy of the file, you want to share the file, only then the hard links are created. If you copy a file that's a separate copy, it's not a hard link anymore. It's not shared. So it means that the changes by different users are associated with their own copies. It's not visible to the other user. There are some file systems called copy and write file systems. Just like you have copy and write memory that we discussed last time for super pages, right? Similarly, you can have copy and write file systems where you don't want to use up too much space on the disk. So you keep one copy, but mark it read only. And when one of the users tries to write to it, then you just make copies of the parts of the file that were modified. So you can have copy and write file systems to save space, but they're usually worse from performance perspective because write operations become more expensive. You have to make a copy. So that's possible, but generally speaking, when you copy a file, you really are occupying more space on the disk. Okay. All right. Any other questions so far? Okay, very good. So I'm glad to know people are listening. Okay, so this is a cool feature that came with Unix, and it's still widely used in Unix systems. So now we're going to look at we have some idea what a file system does now, but we're going to have a more formal definition of it. So file system is responsible for managing two things: data and metadata. So data refers to the data that you want to store, like for example your music files or text files or video files or whatever else you have that you want to store. All right. Whereas but then data by itself is meaningless. Like I mentioned earlier, in Unix, the file itself doesn't have any semantic structure or meaning from OS point of view. So if I give you a file, which is a sequence of bytes, and I say, here's a file, and you'll say, what is this file? What does it contain? Right? You need more information about the file. Of course, the name and ownership and all that stuff, but also what kind of data is in there, and also where can you find the contents of the file. So this additional information about the data, it's called metadata. So metadata describes the data. So for example, if it's a music file, then what is the encoding format, how do you play it, and all that stuff. What software should you use to play it? So these are attributes, the attributes of a file, properties of a file. They're called metadata. Metadata is really important because without metadata, you can't do anything with the file. In order to use a file, to edit a text file, you need to know it's a text file. To play a music file, you need to know that it's a music file, right? So both are important. So the file system spends a lot of time, a lot of effort maintaining both the metadata and the data. So the file system is responsible for, so I'm reading the last set of bullets here. It defines the format of the data objects, and it stores those data objects. It defines the format and meaning of the metadata associated with the data objects. So for example, file name, permissions, size of the file, type of the file, all that stuff. But it goes beyond that. It's also responsible for storing the data, storing the content of the files on the storage system. So if you create a large file, for example, I'm recording this lecture, right? So it's getting recorded into a file somewhere. So the location of the individual data blocks on the storage device, the hard disk, right? Where are those blocks located on the disk? So that if later somebody wants to go access those files, they have to be retrieved from the correct location. And file system is responsible for tracking the location of these data objects. And finally, it may not be obvious, but then you don't just have to manage the data occupied by files, you also need to manage the free space, right? So if I want to create a new file, I need to know where is the free space on the disk that I can use for the new file. So which means that I should be tracking the free space and so that I can use them when I need it, okay? So it's really important for file system to track the free space as well, okay? So the question is, so metadata is like a file extension. File extensions like say .txt or .mp3 or .mpeg, they're historically used to represent the type of the file, right? But from the file system's point of view, the extension is just a part of a file name. Like you can take a text file and name it .mp3. That doesn't change the content of the file, right? Internally, as part of metadata, you may store a type of the file. And if you take a generic Unix file system, the type is just some information that is made available to user-space programs so that they can do something with it. As far as the OS is concerned, the type is meaningless. It doesn't do anything with it. So yeah, the type of the file is a piece of information that's stored with the file as part of metadata, but the OS doesn't do anything with it. It's up to the user space programs to look at the metadata and to figure out what to do with the file. Does that make sense? Okay. All right. So, so a related concept, and this is not specifically covered in the paper, but it is part of most modern file systems, is this idea of a virtual file system. So what does that mean? We talked about virtual memory, and now you see virtual file system. The idea here is that there are many different types of file systems. not just many different types of files. There are many different file systems, right? What this means is that, over the years, for handling different performance and storage requirements, people have invented different file systems. For example, in Unix, you have ext4 file system. Before that, there was ext3 and ext2 file system. There are other types of file system. For example, for flash drives, you may have a file system. For CD-ROMs, there may be a different file system. So if you look under the Linux source tree, there are hundreds of file systems out there. Okay, now, and each file system has its own unique purpose. Now if you're a programmer writing code to access a file, and let's say you don't know in advance what type of file system your data will be stored in, then it will become very hard for you if each file system provided its own system calls, its own interfaces for its programs. Then it will be very hard for a programmer to write a version of the program for each type of file system. You don't want to write like 100 different versions of your user space code, one for each type of file system, right? That's why there's a uniform interface provided by virtual file system. So inside the OS, there are many implementations of file systems, but they all register themselves with this virtual file system, which forms a common layer on top of all the file systems. So these system calls that you have been using, read, write, open, close, right? So these system calls are provided, they're part of the virtual file system. And underneath, virtual file system allows other file systems to register themselves. So when you make a read system call, the virtual file system will look at which file system handles this file, and then make the corresponding read system call for the corresponding file system. So like you're writing a miscellaneous character device, in a sense, you could think of it as writing a file system, right, for that miscellaneous character device. So when the read system call happens on your /dev process list character device, then the read system call is redirected through VFS to your read system read function inside your kernel module, right? So in a sense, you're kind of writing a small piece of a file system. Isn't that cool? So pretty much all the file systems do that. They provide their own read-write functions or open-close functions, but then they all tie into the virtual file system against which all the applications are written. Okay. So, and underneath all these file systems is the file system cache. So if you read a piece of data, and this cache usually applies to block devices, not character devices, like the one you're developing. But for block devices, if you read a piece of data from a disk or a CD-ROM drive, for example, it would be stored temporarily in the cache. So if you access the same piece of data again, you can reuse it. This cache isn't the main memory. It's not a hardware cache. This is an OS cache. It's kept in the main memory. And under the file system cache, there are device drivers that know how to talk to the lower level devices, whether it's disk or CD-ROM or USB or any other type of IO device. Okay, so this kind of a storage stack, right, from hardware through multiple layers of file systems to the system call and finally user level application. Any questions so far? Okay, so I'm going to move on to the next slide, which is we're looking at now the organization of storage device, specifically a block device. So, and I will, as I mentioned earlier when we were talking about kernel programming, about kernel modules, there are different types of devices, character and block devices. In block devices, data is read in fixed units, like 4 kilobytes or 8 kilobytes, just like pages in the memory. So if you take a typical hard disk or any storage device, you can think of the storage as like a giant array. Like, always everything is an array. Page tables are an array, and the storage devices are an array. So you can think of it as an array, like it's shown in this picture here, where there are blocks of data starting from index 0, block number 0, block number 1, and so on, till whatever is the size of the disk. And given this array, you can partition this storage device into many partitions. So in this example, we have shown that the initial part of the disk here is something called MBR, master boot record, which if you're using a storage device as a boot drive, then the BIOS would first go to the MBR, and then it would say which file system, which partition has a bootable operating system, and then it will jump to the corresponding operating system and then boot your system from there. Okay, so that's the master boot record. And then there's a partition table that tells you how many partitions are there. Partitions, as the name suggests, you divide up the disk into fixed size partitions, and you format them into a specific file system type, and then you can store your files in them. So here we have divided up into like 3 file systems, file system 1, 2, and 3. And within each partition, you can then, it encapsulates an entire file system. Okay, so you can have like a NTFS on one partition, ext4 on another partition, and whatever else you want on other partitions. So, or you could have like multiple partitions of the same file system type. But what that means is that a single partition is a self-contained unit for a file system. And then there is a zoom in of, within a partition. It's like a typical organization. Again, all file systems may not look like this, but within the file system, you may have a boot block that has some code where you can boot your OS, from which you can boot your OS. And then there may be a super block, which is like the very first inode it contains some initial information about the rest of the file system. For example, the initial inode for the root directory, and then where you can find the other parts of the file system. I mentioned free space management. There is some part of the file system dedicated to storing or tracking information of free blocks. There are inodes. We'll talk in detail about those. They describe individual files. So for every file, you will have an inode in your file system. And then there's the contents of the root directory, then subdirectories and individual files and so on. Okay, different file systems may have different organization, but this kind of gives you a high level view of what a file system may look like. Okay, any questions so far? So where does metadata located in the file system layout? From Satrio. So metadata is part of is stored in inodes, or inodes, you could think of it as information nodes, right? So or index nodes, sorry, not information node, index node. It has all the information, like the size of the file, type of the file, permissions, all that stuff. And then the most important part is where can you find the contents of the file. So we'll look at the structure of a typical Unix inode in a little bit. But essentially, those are part of the inodes. Now, here in this picture, it's shown as if inodes are located in one place together. But actually, inodes could also be spread out over the whole disk, right? So you may have some central data structure that keeps track of where the inodes are, and then the inode themselves could be stored across the disk. Just like page tables for memory, inodes are like page tables for files. So just like page table itself can be spread out over the memory, similarly, inode itself can be spread out over the disk. Does that make sense? Okay. All right, let me just check how we are doing with time. 5:30. You guys are awesome. So let's, so I'm going to assume that if anyone wants to take a break, they would go ahead and do so. So I'm not going to necessarily stop the lecture. It's also being recorded, so if you miss something, you can always look at the recorded lecture. Okay. All right, so now we're going to look at the most important function of an inode, which is how do you keep track of the contents of a file. Okay, so let's start from a simple naive way. Let's say we are asked to write a file system, and as part of that we have to keep track of the location contents of a file on the disk. Okay, so a simple approach could be that, let's say we have files A, B, C, D, E, F, and so on, and we store them on the disk one at a time. So first there are 4 blocks of file A, 3 blocks of file B, then 6 blocks of file C, and 5 blocks of file D, and so on, one after another. And they're all stacked against each other. And since we're going to treat the disk like an array of blocks, so if we want to access file A, we access blocks 0, 1, 2, 3, and the file B is blocks 4, 5, 6, and so on. Okay, so it's very simple, and it's also convenient because if I have a user space process that wants to access, say, the 4th block of file C, all my file system needs to know is that file C here, it starts from block number 7, right? And then the 4th block from there, I could just index into that block and fetch it, right? So I don't have to necessarily search through all the blocks. It's like constant time access for both read and write operations. Okay, so it's very convenient for read-write operations. But then there is a problem, which is fragmentation, because different files are of different sizes. So if, for example, we delete file D and then I delete file F, then I have these 2 blocks, 5 free blocks and 6 free blocks, that are stuck between other files, right? So if I want to create, let's say my disk is otherwise full now, I want to create a file of, say, 10 free blocks. There's space there, but there's just not next to each other, right? This is the problem of external fragmentation. You have free space, just not contiguous free space. So I could then do some expensive operation, like some of you may have done defragmentation on Windows operating system, and if you know what I mean, that's basically takes files from one end of the disk, moves them to another, and keeps doing that for like an hour or so till you have all your free spaces on one side, all your files are on the other side. So you could do defragmentation, move all the files to one side and free space to another. There's also another term for this called compaction. If you do that, then you get back your free space and you can use it for new files, but that's of course expensive. Even for memory, defragmentation is expensive. So for disk, it's even more expensive because it's slower. Okay, so we want to be able to, the main problem is that all the contents of a file together. So what if we could store the contents of a file all over the place and then find them as we need them? Okay, so one idea, the natural idea to do this is called the linked list, right? So we could say, all right, let's make a linked list. We don't want all the blocks together next to each other, so we'll have block 0, but we'll take a few bytes at the top of the block to store a pointer, which is the block address of the next block. Okay, so in this example for file A, logical block 0 is located in physical block 4, and then logical block 1 is located in physical block 1, and 2 is located in 2, 3 is located in 10, and so on. And at the top of each block, there's the block address of the next block, right? So the pointer there, it's not a memory pointer, it's like a pointer to, it's the block address of the next block. So for 4, the pointer is actually 7. For 7, the pointer at the top is 2, and so on. So if you do this, then now we have the freedom that whenever we want to create a file, we could just pick free blocks wherever they are, and we could link them together in a linked list. Okay, and our file could grow and shrink as need be. Like in the previous case, once we create a file and the next space gets occupied, we can't grow and shrink it. Okay, now with this case, we can grow and shrink it. So this is really nice, right? And likewise, file B has its own linked list, and every file has its own linked list. But now let's go back to what was good about the previous thing. We had the ability to do constant time access to any single block, right? But now if I want to say update block 4 of file A, I can't just index into it like I did in the previous case. I have to first find the starting of the file, block 0, then go to block 1 and block 2 and so on until I reach block 4. Then I can do my read or write operation, okay? And likewise, if I want to like delete some part of the file, then that's going to be problematic in any case. So so basically our access, read-write accesses are not constant time anymore, okay? So that's not nice. Although now we got rid of external fragmentation problem, our read-writes are not constant time. So there's a question from Aditya, how is file block decided? How are they actually allocated? Again, file blocks could be decided by the operating system, by the file system itself. Just like for pages, there is a default size, which is usually it matches the page size, because when you read data from a file, it has to go into a page. So usually it's like 4 kilobytes, but you can have larger block sizes for certain files, like 8 kilobyte and so on. And that block size may be further mapped down by the hardware, by the disk controller or the firmware on the disk to say sector sizes or smaller units. So the question is, so there can be a problem of internal fragmentation here as well. You mean for the linked list case, you're saying you could again have a problem of internal fragmentation. Yeah, internal certainly, because you could have a block that's only partially used and the rest of it is not used. That's right. So that's by nature, whenever you do memory allocation at the granularity of more than a byte, right, you're going to have internal fragmentation. So the only time you can't have internal fragmentation if your memory allocation granularity is 1 byte. So the moment you have a page, you're going to have internal fragmentation. But you can't have external fragmentation anymore, like we did in the previous case. Does that make sense? Okay. So what we would ideally want, so there's another problem here though, that the pointers that you see at the top of each block, that's metadata, right? It's not a content of the file. User doesn't care about that. It's actually telling you what's the location of the next block. And now we are mixing data and metadata in a single block. So think about it, like user space program that's running on the CPU, it has some content in memory in a 4 kilobyte page, and then it wants to write it to a block on the disk. Okay, and let's say the block on the disk is also 4 kilobytes. Now, when you try to write a 4 kilobyte page, actually you have to leave out the few bits, because the top few bits, like 4 bytes or whatever, they're needed for a pointer. So your whole page can't fit on a disk block. For the extra few bytes, you need to allocate another disk block where you hold the remaining bytes. Okay, so a single page in memory now becomes 2 blocks on the disk, right? And depending on how your file system allocates these blocks, you might end up having more internal fragmentation. Or if you mix content from different pages in memory in the same block, then you have to keep track of where the memory page boundaries are. So if you can follow what I'm saying, that when the content of a page can't fit inside a single block, so that leads to additional complexity. So the core reason is that we are mixing data and metadata, right? We don't want to do that. So we want to be able to maintain the separation of data and metadata. So we're going to first look at this problem, the problem I just described. How we can separate data and metadata, and then we can go back to the issue of constant time access that we had with the original scheme. All right. Okay. So yeah, so advantage, we have locally contiguous blocks can be now discontiguous, so no external fragmentation, but then random seeks are expensive. So now you have to start from the beginning and then traverse to the necessary location to perform read and write operations. So next we're going to look at how we can separate the data and metadata. So the idea here is that you don't want to store linked lists inside the blocks, but rather you want to store them somewhere else. So you might have heard of this FAT file system, FAT, right? Whenever you're dealing with Windows systems, you're usually come across this term. Do you want to format it as a FAT file system? FAT there stands for File Allocation Table, right? File Allocation Table, which is a fancy way of saying that I'm going to store a linked list inside an array. Okay, so so here is an example of a file allocation table, which is again an array. So in this file allocation table, you have one entry for every block on the disk. So if you're, let's say a theoretical disk here has 16 blocks, then the file allocation table is indexed from 0 through 15, right? And we have two files, A and B, stored on the disk somewhere. So we have a pointer somewhere that says file A starts from physical block number 4. Okay, so block 0 is at physical block number 4. And then that entry there says 7. What that means is the next block is at physical block number 7. Okay, so so if you're traversing the file, the linked list from the previous picture, you would start from entry number 4, then you look up next block is at 7, then you go to 7, and then you see that the entry there is 2. So it says the next block is at physical block 2, then you go to 2, the next block is at 10. If you go to 10, the next block is at 12, then you go to 12, then that's the end of the file. So there we have -1, meaning there are no more blocks, right? So we have basically stored a linked list inside the file allocation table, and we know the start of file A somewhere, and that allows us to traverse the linked list. Okay, so the actual physical blocks are separate from this linked list. They're somewhere on the disk, right? Block number 4, 7, 2, and so on. So now what that means is that the page in memory will match the page on the disk, the block on the disk. So you don't have to like break up a page to be stored on 2 blocks like we had to do in the previous slide. Likewise, file B has its own linked list, and file C would have its own linked list, and so on. So you get the benefit of having a linked list. You have no external fragmentation. Also, it's fairly simple to develop something like this, a file system like this. And but of course, we'd still have that seek problem that we had. So if to access, say, a 4th block of file A, we have to start from the beginning of the linked list, traverse through the linked list to find the corresponding block. So it doesn't give us constant time access still, but at least it separates data and metadata. Okay, so we will try to solve the other problem next. Any questions so far? Okay. So, so of course, it turns out that Richie Thompson and Richie had foreseen these issues, and in their original Unix system, they proposed this idea of an inode or an index node, which stores all the metadata corresponding to a file. So every file will have an inode, just like every process has a page table. Similarly, every file has an inode. Okay, and inode will describe various attributes of the file, but most importantly, it tells you where to find the contents of the file. Where are the individual blocks stored on the disk? Okay, so just like page table provides a mapping from virtual page number to physical page number. Likewise, inode provides a mapping from logical block number to a physical block number. Okay, whatever page table does for virtual memory to physical memory mapping, similarly, inode provides you a virtual block number of a file to the physical block number on the disk. Okay. From a user's point of view, a file starts from byte 0 and goes up to some maximum limit. Similarly, but then these logical byte addresses have to be relocated to physical block numbers on the disk, just like for a normal page table in memory. So inodes are providing you that mapping. So we're kind of looking at page table for files. All right, so that's a good way to think about it. And just like with page tables, we saw that page tables were just an array of virtual block numbers, virtual page numbers to physical page number, right? Similarly, you can think of inodes as an array also, okay? But with different design requirements that we will take a look at in a little bit. Okay, is that clear? Any questions on this basic idea? Like what inodes are doing? What are inodes responsible for? Okay, so let's go further. So again, I took two pictures here. Okay, yeah, Bobby, you have a question. Yeah, go ahead. Okay, I'm assuming he's typing a question, or you could speak if you dare to. Okay, I'm gonna proceed. Okay, so in project 2, I can't remember what function it was, but one had to have inode type as a parameter. Ah, I see. One had to have inode type as a parameter. What was it for? I don't remember either, actually. I'm very bad at remembering the API details. It was the open function. Okay. All right. Yeah, I don't know the answer right now. I will have to go look it up. But if you can remind me at some point if I forget. Okay, that would be nice. Yeah, thank you. So, yeah. So here, we are describing, showing the data structure. The whole thing is described, shown here as an inode. From the left to the right, the whole thing is a single inode, all right, for a single file. And then the same picture is also described in the next slide, which looks more scary, but it conveys the same concept. The whole thing is one inode for one file. Okay, so, and they're from two different books. The previous one is from Silberscheidt and Galvin book, and the other one is from Tenenbaum's book. So I'm going to go back here. So as I mentioned, inode itself describes the properties of a file, and inode itself is stored on the disk. There is a question from Shengdong Wang. What is the abstraction for open? That is an abstraction. Okay, it's a comment, not a question. I see. So going back to my discussion, so inode itself is stored on the disk, just like page table helps you find virtual to physical page mapping, but page table is stored in memory. Likewise, inode is stored on the physical disk. Okay, so so here, we have in the first block on the left side, you have various properties like what is the mode of the file, and then protection attributes, the readable, writable, executable, and all that stuff. Who are the owners of the file, timestamp, when was the file created, when was it updated, when was it accessed, and all that things. Some file systems, some files may have different block sizes. So in this case, you can have a block size as a property. Reference count that we talked about earlier for shared files, that's another. So these are just some of the properties, and usually there are hundreds of properties for a file. So if you look under information for any file, on Unix system, you can do ls -l, and it will give you a whole bunch of attributes for a file. Likewise, on every other operating system, you can look up the information for a file. So that's showing you metadata for the file. So following all these properties, there is this information on where can you find the file on the disk, okay? And so if you think of the inode as being an array, so for block number 0, I want to look up index 0, and that will give me the physical block number, right? And then for block number 1, I want to look up index 1, it will give me the physical block number. So if you treat that as an array, then it's very easy to understand. So the part that's marked direct blocks here, that's the initial part of the array, okay? So, and then if your file is larger than the number of entries in the direct blocks, then there's a single indirect block that points to a bunch of direct block addresses, which then point to the direct blocks. So, and then there's a double indirect and triple indirect. So what this means is the reason it's structured like this and not like the page table that we saw for virtual memory is that so over time, the people observed that most of the files that people create are small files. That may be changing now because there's so much media files that are being created, like audio and video files. But traditionally, if you take a look at text files or emails, right, or your text messages, for example, these are all small files, right? And most of the files people store on the disk are very small files, like few kilobytes or at most few megabytes, right? So, and for these files, and you don't need a whole lot of mappings. You don't need a whole lot of logical to physical block address mappings for those. So those could be directly stored in the direct block addresses. So if so typically, for example, there may be 10 to 13 direct block addresses in an inode. So and each block address will point to one data block, like one 4 kilobyte data block. So if I had 13 4 kilobyte data blocks, then I will have 13 times 4 KB worth of file that I can index, right? So, with what is 13 times 4 kilobytes, 52 kilobytes, right? So if your file size is less than 52 kilobytes, you can access them directly through the direct block address. And if you, and that's like constant time lookup, like there's no search involved like with the linked list. And then if your file size is more than 52 kilobytes, then you can have a single indirect block that points to another block that contains a whole lot of direct block addresses. And how many direct block addresses are you getting from the single indirect block? Gee, that's a 4 kilobyte block, and each block, let's say 4 bytes. Then you have like 1024 4-byte address, direct block addresses. So the single indirect block is giving you 1024 direct block addresses, each of which points to a 4 KB data block, right? So you're kind of an exponential, super exponential increase from direct block to single indirect block. So if your file size is more than 52 kilobytes, then you use the single indirect block, and then it will give you access to direct block addresses, okay? So that gives you another 4 megabytes worth of data. And if you run out of those, if your file is more than 4 megabytes plus 50 kilobytes, then you can go to the double indirect block, which gives you access to a single indirect block, each of which points to direct block addresses, which then give you access to the block. And then if you're still not happy, you can go to triple indirect block, right? So, but the key thing is that whatever is the level that you go to, there's no search involved. There's constant time access, depending upon the size of the file, of course, but you either do 1 lookup or 2 lookups or 3 or 4 max, right? And then you have access to your file, which is pretty nice. But most of the time, most of your files will be small and you'll be happy with direct block addresses. So this is an example of the principle in computer science called making the common case fast. Whenever you're designing a complex system, there are certain features of it that will be used often. There are certain features that won't be used often. So you want to spend a lot of time making the common case, the most often used case, fast, more efficient, and having higher performance. And then the other boundary cases, like in this case, the boundary case is having a really large file. Like very rarely people create a 1 terabyte file. But if you want to create it, this Unix inode will let you create it and store it. But most of the time you don't need it. So it's okay to have a slow access to a 1 terabyte file, so to speak. Okay, so so that's the idea behind the Unix inode. Any questions so far? Does any of this not make sense? Any comments? So if you think about this, like the way inode is structured versus a page table is structured for virtual memory, they look different. In a page table, we had a page directory followed by second level page table, right? Whereas in inode, we have direct block addresses, then single indirect, double indirect, and so on. But they're both arrays. Inodes and page table both are arrays that do logical or virtual to physical mapping, right? But then they have different structures. Why? Because first of all, in the case of virtual memory, all processes get 4 gigabyte memory, right? It doesn't matter 4 gigabyte of virtual address space or whatever is the architecture allows it to do. Whereas file sizes can be different. You can have small files, large files. You can have small files that grow into large files over time. So the way they are used, the purpose for which they are used is different. That's why, although at a conceptual level, they're serving the same purpose, but their actual implementation and design is different. So again, it's worth keeping in mind the whole inode is one file. It's for one file, right? Of course, the data blocks shown in this, earlier I said the whole thing is one inode. I was slightly wrong. The data blocks shown here are not part of the inode. The last part of the tree here. Just the addresses, the block address part is part of the inode. But the whole thing is for one file. Okay. All right. I'm going to check the time again. It's 6. Let me just cover a few more things, and then we'll call it a day. So this is again the same picture but from Tenenbaum's book, and it covers the same concept. One of the things I didn't mention is that you don't have to allocate the whole inode at once. You can let it grow dynamically. So when you have your file is small in the beginning, you only use direct block addresses. When it grows beyond say 52 kilobytes, then you can use single indirect block, and then the inode can grow as the file grows. So, and different parts of this inode, different levels of this inode, they can be stored in different parts of the disk. They all don't have to be together, right? So, which again helps with avoiding external fragmentation. Okay. So, all right. So one of the things they mention in the, like right now you're creating character devices and an entry gets created under /dev. And who came up with this idea? Well, Ritchie and Thomson did in 1960s. And we are still using their original idea, right? So what that means is any IO device shows up under /dev as a regular file. And it has properties like a regular file, and it has an inode like a regular file. And you can do read and write requests through the virtual file system like a regular file. And so you have the same interface, and you can use the same protection mechanisms. So if you want to allow a certain device to be read-only and not readable and writable, you can enforce that using the standard file system interface and access control policies. So this simplifies a programmer's life a lot, right? You can write an application that works for one type of device and then use it for another type of device, hopefully without much changes. Okay, so this was another innovation from the Unix that wasn't there before then. Uh, and then there's this idea of a removable file system. Earlier we saw a file system hierarchy tree where there was root directory, subdirectory, and so on. So what these guys said was that this entire file system doesn't have to be on a single disk. Actually, let's say you may have two disks with two different file systems, right? You could mount a new file system on a new storage disk under an existing single rooted file system hierarchy. So there's a mount command, for example, using which you can mount an existing file system under a new file system under an existing tree. And that's very convenient because sometimes, for example, you might bring in another hard disk and you might, or sometimes you might, for example, plug in an external disk through your USB port or HDMI port. And what does it do? Well, it mounts your file system into your existing, the new file system under the existing file system. And you can view the new storage device as part of your existing file system hierarchy. And when you're done with it, you can unmount it, like what you call the eject functionality. It's essentially doing the unmount operation, reverse of mount operation, right? So this is, again, it came from the original Unix system developed by Ritchie and Thompson, right? The other interesting property, which may not be obvious, is that we talked about shared files or hard links earlier. But if you're going to mount a file system from another storage device, hard links are not allowed across mounted file systems. So they may look like they're part of the same rooted hierarchy tree, but then you can't have a hard link from one file system to another file system. And you can think about why that's disallowed. I'm going to leave that as like a research question for you to find out if you're curious. Okay. Then there are various protection bits. You know, I'm not gonna go into the details, but generally there's like user, group, and others. And users can have read, write, execute permissions. Group can have read, write, execute permissions, and likewise for others. And then there's another bit called a set user ID bit, which allows a program to change its effective user to another user when it's. So there are a lot of low-level, hairy details. Which if there's something that Unix got wrong was this permission mechanism. So this is also the access control mechanism, protection mechanism. It was very easy to get this wrong, to get these settings wrong. A system administrator may set these bits incorrectly and the whole system is compromised for certain critical files. So it has been a source of vulnerabilities for many years, and people have come up with alternative access control policies over the time, but the original protection mechanism still persists as the default mechanism. All right, these are some of the system calls that you're already familiar with: open, close, read, write. But you can see that the original interfaces were slightly well, these were not quite that different. They're still pretty much the same. Like open has a name and flags, read has a file pointer, buffer, and count. Instead of a file descriptor, you had a file pointer instead. And likewise for seek, but now you have lseek and so forth. But the basic abstractions, system calls are still the same. Okay. And in the paper, they also describe other system calls they developed for Unix: fork, pipe, wait, exit, all the things that you used in your first assignment for your shell. These were originally devised by Ritchie and Thompson long ago. And then they developed an entire interactive shell where you could type in your commands, just like your assignment one, which you had such a, which I gave you such a hard time. So these guys first came up with this idea of a shell. IO redirection came from that. Pipes, the filters, chain of commands came from that. You can run processes concurrently. You could run processes in background, foreground, combination of these. Pretty cool for a system that was developed in the 1960s. Okay. And at this point, I will stop. Next is the discussion of file system caching, and I'm not going to rush it right now, but we'll continue on Wednesday. Any questions anyone has before we stop? Okay, so again, if you have questions, feel free to ask me. I'm going to keep my original schedule and treat the next hour as an office hour. So I will kind of then turn it into the office hour, turn this session into an office hour mode after this. And if you have questions, feel free to talk to me. Okay? All right. Thanks. Have a good evening. Have a good night.